Welcome to ePG Pathshala lecture series on data analytics. In this session, we will be continuing with dimensionality reduction techniques. In the previous session, we learnt about singular value decomposition. As part of this session, we will continue with singular value decomposition with a case study, and then we will discuss about another decomposition technique called CUR, which is a matrix approximation technique. So, the objectives of today's session are to understand SVD using a case study, learn the process of CUR approximation technique, and then know the performance between SVD and CUR. The way in which the slides are organized are as given in this slide. First, let us start with a case study for SVD, then understand how querying can be done with the help of the reduced dimensions, know about the drawbacks for SVD, learn the steps involved in CUR approximation techniques, and finally compare SVD and CUR dimensionality reduction techniques. Now, let us start with a case study for SVD technique and then learn how to query. Consider the given set of documents. The given set of documents are 3 in number: document D1, document D2 and then document D3. The document D1 contains the following statement: shipment of gold damaged in a fire. Document D2 contains the following statement: delivery of silver arrived in a silver truck, and document D3 comprises of the statement: shipment of gold arrived in a truck. Now, our objective is to represent these documents in the form of a matrix, say a document term matrix, and then use the document term matrix for querying. For example, if you have a query which has the following terms: gold, silver, truck. Now, you are going to apply the given query on the collection of these documents. Now, instead of we working on a larger dimension, let us understand how we reduce the dimension and then work with respect to the given query. Now, the given set of documents D1 is going to be represented using a set of terms. The terms are A, arrived, damage, delivery, etc., etc. So, the terms that are available in the given 3 documents are sorted in alphabetical order. Now, we can represent the given 3 documents as a vector of these terms. Now, consider the vector which represents document 1. Vector 1 actually indicates whether a particular term is present in the document or not. If present, it indicates how many number of times that particular term has occurred. For example, for document D1, we find a value 1 for the term A, meaning the term A has occurred once in the given document D1. Now, consider for document 2, consider the term silver. The term silver has occurred 2 number of times in document D2. Therefore, we have a value 2. In this fashion, we represent the 3 documents D1, D2 and D3 as a matrix. Now, let us assume this matrix as our original matrix A. Now, what is that we are going to do is, we are going to represent the given query silver, gold, silver, truck, and we are going to identify from the given matrix A what are the documents that are relevant to the given query Q. So, the given query Q is also represented as a vector of terms. So, there we may find the terms gold occurring once, silver occurring once and the term truck occurring once, which forms the query. The rest of the elements will be filled with zeros. Having understood given documents represented using a matrix A, now let us analyze how this is going to be done using a dimensionality reduction SVD. So, as discussed earlier, we are going to decompose the given matrix A into 3 sub matrices U, singular matrix S and then the V transpose matrix. Since we have discussed the steps involved in computing U, S and V in the previous session, now we are not going to discuss in detail about this. Instead, we assume that this is the U matrix which is derived, this is the S matrix and V transpose matrix. Now, take a look at the dimension. There were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11 number of rows, 3 columns. So, the dimension is 11 by 3. For the singular value matrix, it is going to be 3 by 3, and similarly for the V transpose matrix, it is going to be 3 by 3. Once you have the U, V and then the S matrix, you can now work on the reduced dimensions by choosing the value for k. Now, assume we have chosen the value for k as 2, meaning for the given U matrix, you will have to choose only 2 columns. For the given S matrix, you will have to work on only 2 of the singular values, and for the given matrix V transpose, we need to work only on 2 rows, the third row will be ignored. So, now what happens is the reduced U matrix, the reduced singular value matrix and the reduced V transpose matrix are shown like this. Now, let us understand how querying can be incorporated and use the query for the purpose of identifying similar documents. If the query is represented as a vector as shown in the previous slide, now all that you need to do is you need to understand how to compare one document with respect to the other document and using the query. So, suppose D is equal to D transpose UK and then the inverse of the singular value matrix, then you can represent Q using the same equation Q transpose UK and then singular value inverse. So, the transpose for the Q matrix is this value, the UK matrix is the reduced U matrix and the S inverse is the inverse of the 2 dimensional singular value matrix. Now, once the query, the reduced U and S matrices are there, now you can represent the Q matrix in the form of a vector. So, the 2 dimensional vector for the given query Q is now equal to minus 0.214 and minus 0.182. This is derived by multiplying the 3 matrices, that is the Q transpose matrix, U reduced U matrix and then the reduced singular value matrix. Similarly, the documents can also be represented as a 2 dimensional vectors. Now, what is that we can do is we can take these 2 dimensional points and then if you plot it, you can have a 2 dimensional scatter plot. Having known these documents and the query as a 2 dimensional information, now you can make use of a simple cosine similarity metric for the purpose of understanding what are the documents that are similar. So, the cosine similarity metric is defined as shown here. So, similarity between query and the given document D is equal to Q, the scalar product of Q and D divided by the absolute value of Q and D. Now, let us take the given query and document D1. Now, this Q dot D is the first component in Q and the first component in D are multiplied. So, x1 multiplied by x2 plus y1 multiplied by y2, the whole divided by square root of x1 square and y1 square multiplied by square root of x2 square y2 square. This equation will result in a value of minus 0.0541. Similarly, we calculate the similarities between query and document 2, query and document 3. Now, when you take a look at these values, so this is the similarity value between query and document 1, this is the similarity value between query and document 2 and this is the similarity value between query and document 3. Now, when you take a look at this value, you will find the similarity value is high for query and document 2 by means of the value 0.99. Then the next document which is highly similar with respect to the given query is indicated by this second largest similarity value 0.4478, and the least similar document with respect to the given query is document D1 highlighted by a negative value. So, now what we can do is, now we can rank the documents in descending order, which states that D2 is highly similar with respect to the given query when compared with document D3 and D1. So, document D2 is highly similar, next highly similar value is document D3 and the least similar is document D1. Having understood this, now we can easily conclude what may be the correct document which will be retrieved as a result for the input query gold, silver, truck. So, we can easily say that document D2 is highly similar. Now, if these two dimensional parameters are plotted and highlighted as shown in this scatter plot, now we may be in a position to find these dots indicate the respective documents. So, document D1 is represented using this two dimensional value, document D2 with this value, document D3 with this value, and the query given query Q is represented using this value. Now, from this diagram itself you can easily see to which of these three documents the query document is very close, which is computed based on the angle. So, now you can find query Q is very close to document D2, the vector D2 rather than document D3 and D1. When you compare between D3 and D1, query 2 is similar to D3 rather than D1. So, now this gives us an idea that document D2 scores higher than document D3 and D1, and hence the vector, that is document D2 vector, is very close with respect to the given query vector. So, the previous results that we discussed and the scatter plot or the two dimensional representation of the document vectors also clearly indicates that document D2 is the correct or relevant answer for the given query. Now, this is a place where you should understand clearly how the reduced dimensions are useful. So, instead of you working on the actual U, actual singular value matrix and actual V transpose matrix, here we have worked on a very reduced dimension of the U matrix and S matrix, and this is a place where dimensionality reduction has happened, and accordingly the quantum of data on which we are analyzing is reduced to a larger extent. So, with this case study we might have understood clearly how singular value decomposition will help us in reducing the size of data on which we are trying to analyze, and also use it further for many applications like querying. Though this technique provides you a reduced data set, still there are certain drawbacks. The drawbacks are in terms of the resulting matrix, which will be derived by multiplying the U matrix, the singular value matrix and then the V transpose matrix, which is going to be an approximation, and the rank of that approximation is going to be low. Therefore, interpretability with respect to the given matrix becomes a bit difficult. The singular vectors actually specifies a linear combination of all inputs of the column or the row. Therefore, interpreting the columns and row becomes a bit difficult, and also it lacks sparsity. Singular values are dense in nature. These three important drawbacks actually will result in, say, reducing the complexity of the given singular matrix, and hence certain amount of error will be introduced. Now, let us understand how these errors may be overcome using another dimensionality reduction technique called CUR, which is a matrix decomposition or approximation technique. The goal of CUR is same as SVD technique. Here also we are trying to decompose the given matrix A into C matrix, U matrix and then the R matrix, and then there are various constraints on the C and R matrix. Ultimately, the objective is the difference between the original matrix A and the product of CUR must be minimal. This must be the main objective. When you decompose the original matrix into C, U and R matrix, the U matrix is going to be the pseudo inverse of the intersection of C and R. What do you mean by this is, when you are trying to work with respect to the U matrix, we try to identify what is the intersection. Only those intersection regions alone can be used for analysis, and the rest of the regions can be ignored. Now, let us understand how this CUR matrix may be derived using an algorithm. So, algorithm shown here is used for deriving the C, U and R matrices. So, initially you need to select the data and it must be represented in the form of matrix A, and assume the size of the matrix is m by n, the sample size is C. Now, the output is going to be a matrix called C, whose dimension is going to be m by C. Now, the C is the size of the sample that we require. So, for each and every column, what we are trying to do is we are trying to calculate the probability value, and for each and every sample columns we are selecting an element based on this distribution, probability distribution, and accordingly you calculate the C matrix. Now, this is actually a randomized algorithm, because the same columns can be sampled more than once. Now, when you take a look at the matrix, I told you this U is going to be an intersection, pseudo intersection of the C and R matrix. So, diagrammatically you can see that the intersection of C and R is where the U matrix is going to be highlighted. So, when SVD provides X, Z and say Y transpose matrix, the U matrix is going to be a pseudo intersection of the C and R matrix, assume which is represented using W. So, now Z plus acts as the reciprocals of non-zero singular values, which is the singular values are taken inverse. So, that is the inverse of the original singular values. So, the W plus here is a notation used for indicating the pseudo inverse. So, the singular values whose inverse value are going to be represented by W plus, and therefore, it is called as a pseudo inverse matrix. Now, we will have to understand how CUR proves to be good when compared with SVD. Now, the main objective is, given an input matrix A, all that you need to do is identify which provides better approximation. Better approximation here in the sense, the difference between the original matrix and the reduced dimensions must result in the actual original matrix. In case the approximated matrix that is drawn by multiplying the decomposed matrices, if the error is very high, then the approximation is wrong. So, ultimately we are trying to work towards which of these two technique, whether it is the CUR technique or the SVD technique, going to provide a good level of approximation. So, the CUR technique makes use of the time complexity m by n to achieve an approximate matrix A, and when you take a look at the difference between the A matrix and the CUR product, this is going to be very less when compared with, or less than equal to, when compared with the original matrix A and the reduced matrix A, which is derived from the SVD technique. So, we introduce a value epsilon highlighting the error. So, the theorem which is proven by Dinas et al. Clearly indicates that CUR dimensionality reduction techniques outperforms SVD technique. Let us understand this with an example. Now, in the algorithm of CUR for deriving the C, U and R matrix, when we are selecting C, the order in which selection of C happens is order of k log k divided by epsilon square, and this is based on the columns of A using the column select algorithm. Similarly, when you are trying to select R, this is also done in the order of k log k by epsilon square rows of the original matrix A using the same column select algorithm. Now, what we are trying to do is we are trying to set the U matrix as the inverse of the singular values, which is represented by the W matrix. Then what happens is the CUR error when compared with the SVD error is going to be twice that of the SVD error. Therefore, we can easily say or prove that CUR outperforms SVD. What are the advantages and disadvantages of CUR dimensionality reduction? It is very easy to interpret the original data based on the new vectors that you are deriving, because the basis vectors are actually the actual columns and rows of the original matrix. Similarly, it is sparse in nature. Because of the sparseness, we may not be in a position to handle the data in a shorter time. This may be a drawback, but the sparseness in the given matrix can be reduced by various matrix approximation techniques. Then there is going to be availability of duplicate columns and rows. Availability of duplicate columns and rows will normally increase the time complexity, and therefore, this can act as a drawback for the CUR technique. So, what may be the solution? Whenever I want to eliminate the duplicate rows or columns, how I can do is I will have to construct the U matrix such a way it is so small when compared with the original C matrix. So, you will have to choose the dimensions accordingly. So, once you want to have a small U matrix, how you can achieve this is you can multiply the columns or the rows by the square root of the number of duplicates. Now, what actually you are trying to do is you are trying to scale. So, this scaling up is reducing the number of accesses. So, when you pictorially represent performance of SVD and CUR, in SVD A, both in SVD and CUR, A is going to be a huge sparse matrix, U matrix in SVD is big, similarly the C matrix is big, but the V transpose matrix in SVD technique is dense, but the R matrix in CUR technique is sparse in nature. The sigma, that is a singular value matrix, is sparse and small, but the U matrix in CUR is going to be dense and small. Because of the sparseness in R, there may be a drawback related to the CUR dimensionality reduction technique. Now, all these data, that is SVD, CUR, are all going to work on data that have some level of linearity in terms of the data. But if this linearity assumption is not existing in the given data set, that is the data is going to be a non-linear data, for example an isomap, then the same dimensionality reduction techniques sometimes may not work out effectively, but still then you can apply the same dimensionality reduction techniques by means of building an adjacency graph or a geodesic distance, which is once again going to be a distance graph, or you can make use of principal component analysis of the given graph using pairwise distance matrix. So, initially you need to do some kind of transformation on the original matrix, and then you can apply SVD or the CUR technique, thereby reduce the dimension and then use the reduced dimensions for the purpose of analysis. This is how nonlinear data can be reduced in terms of their dimension using the existing dimensionality reduction techniques. So, to summarize, dimensionality reduction techniques involves mathematical approximations, and dimensionality reduction techniques have their own advantages and disadvantages. So, before choosing a specific dimensionality reduction technique, we will have to be careful about what is the fundamental mathematics involved and what type of data it is. Only then you will be in a position to select the correct dimensionality reduction for the correct data. Thank you.